Okay, welcome back. Last time we discussed prime ideal and maximal ideal. So, let me do a quick review. So, A is a commutative ring with identity. Then we had a bunch of definitions. So, an element is said to be a unit if it has a multiplicative inverse. So if there exists y, so that x times y times x equal to 1. An element is said to be a prime or element or simply a prime if AB equal to X implies that either so if P divides AB, an element P is said to be a prime element. If P divides AB implies P divides A or P divides B. Equivalently, the ideal generated by P is a prime ideal. So an ideal is called a prime ideal if AB belongs to that ideal implies A belongs to that ideal or B belongs to that ideal. Or equivalently, A mod I is an integral domain. And an element is said to be an irreducible. This, for simplicity, we restricted ourselves only to integral domain. So a non-zero non-unit is called irreducible if it cannot be broken further. So if you do write x as A times B, then either A is a unit or B is a unit in A. Then it is called an irreducible. Finally, there's this concept of maximal ideal. So an ideal is called maximal ideal if it doesn't properly is not properly contained in it's not strictly contained, so it is maximal with respect to set theoretic inclusion in ideals. So if there is an ideal J, so the J strictly contains A, then J must be equal to the whole ring. Okay, or equivalently we have seen the maximal ideal if the quotient A mod I is a field. So by definition, prime ideal and maximal ideal not whole ring. So, so the question is, so what is the relation between irreducible and primes that we are going to explore today a little bit? And yeah, every ideal is contained in a maximal ideal, and you can show that using Zorn's, if you assume axiom of choice. An element is said to be, and finally there was also there is this concept of divisor of zero. So an element is said to be a divisor of zero if the element is a non-zero element is said to be a divisor of zero or a zero divisor if there exists another element y such that x times y is zero. So for example, in Z mod 6, z 2 times 3 is 0. So both 2 and 3 are 2 is a divisor of 0. 3 is also a zero divisor. In an integral domain, obviously there cannot be any zero divisor. Then we discussed examples of primes, irreducible, prime ideal, and maximal ideal. Then we saw that 0 is a prime ideal if and only if the ring is an integral domain. 0 is a maximal ideal if and only if the ring is a field. Every maximal ideal, because field is an integral domain, is a field. And the prime ideals of P of Z are 0 because Z is an integral domain, and all the primes P. And the primes P are reducible elements, and they're also prime elements. And all the prime ideal are actually maximal ideal except 0. Then we saw a field fx, then we know field f, and we take the polynomial ring in one variable over fx, then we know it is a PID. And ideal generated by it looks like maximal ideals are of the form x minus b, or more generally, maximal ideals are of the form x minus b, or more generally, it is of the form ax plus b, where a is not equal to 0 and ab are in F. So B is arbitrary, A should be non-zero. For example, the maximal ideals in CXY are of the form x minus A, can be written in the form x minus A and y minus B. Then example of not prime ideal was x square in Fx. That is not a prime ideal because it has divisor of 0, namely x. The image of x bar in Fx mod x square. So then we saw in an integral domain, prime always implies irreducible. Okay, so every non-zero prime element is an irreducible element in an integral domain. And then we ended with the statement that in a PID, every reducible element is prime. So in a PID, prime is equivalent to an element, non-zero element is prime if and only if it is irreducible. Okay, so so A not equal to 0, not equal to B be an irreducible element in a ring A, in a PIDA, not any ring, in a PID principal ideal domain A to show that A is prime, that the ideal generated by A is a prime ideal. So for that, it is enough to show that A is a maximal ideal. So suppose A is contained in M and M is contained in J. Is the ideal A strictly contained in M? Suppose A is contained in M and M is not equal to the whole ring A. Then I have to show M is equal to A, right? So then M is equal to, because it's a PID, the maximal ideal. So we have to show that the ideal A is a maximal ideal. Suppose A is contained in, A is not a maximal ideal, it's contained in M. And M is not equal to the whole ring. So then M is, because the PID, every ideal is principal. So M is generated by single element small m. And the small m is not a unit, because if small m is a unit, then M will become whole ring. And we know that M is not equal to whole ring. So M is not a unit. So A belongs to the ideal generated by M. So A can be written of the form lambda times M for some lambda in A by definition. So we claim is that A equal to, so claim is that lambda is a unit in A. So the question is, why is that? If you think for a moment, if it is not a unit, then what do you get? M is not a unit and lambda is also not a unit. So you are able to write uh, uh, it as a product of two elements. None of them are units. So otherwise, A will not be an irreducible, right? So it will be a contradiction to irreducibility. So that means, so this means, so this implies that M equal to lambda inverse A. So this implies that M belongs to A, and this implies that ideal gen by A is equal to M. So you took any ideal A between, there is no ideal between A and the whole ring. So this implies that A is a maximal ideal. And hence A is prime. So in a PID, every irreducible element, so this is a useful thing, every irreducible element generates a maximal ideal. So in particular, so corollary of this is important corollary. So consider the field Fx. Consider a field. So consider the polynomial ring Fx over the field F if Fx is an irreducible polynomial then Fx mod Fx is a field and contains F. So from F, you can make it more precise. So from F, we have a F to Fx mod Fx. You send any A naught, you send any A to the constant polynomial A. So this is a ring homomorphism. And so Fx is not zero. So as we have explained, F is a, then F has to be and F is not a unit because it's an irreducible polynomial. So degree of F is greater or equal to 1. So degree of Fx is greater or equal to 1. So because it's a non-zero non-unit element, fx, fx mod fx is a field extension of f, right? And for any reducible polynomial, and fx mod fx, of course, and uh, and is a vector space over f. Now, what is the dimension of this vector space? So let's say fx equal to a0 plus a1x plus an x to the power n, where ai belongs to f, n is greater or equal to 1. And then ideal generated by fx, I can also write as x to the power n plus n minus 1, x to the power n minus 1 plus a. Uh, so, I can write p n minus 1 x to the power pn minus 1 x to the power n minus 1 plus b1x plus b0, where bi equal to ai by an, right? So so an is not equal to 0 because we assume it's a degree n polynomial, so an not equal to 0. Otherwise, you write it genuinely like an minus 1 is. So fx is generated by this. So then it is easy to say fx mod fx. This uh, vector space over f is generated by 1 bar x bar up to x to the power n minus 1 bar. Thus, fx by fx is a field extension of f of vector space dimension equal to the degree of fx. Okay, so this is one way to. So we saw that in a PID, every irreducible element generates a maximal ideal, and we apply this to the PID polynomial ring. Then you take a irreducible polynomial, and without loss of generality, we can assume it to be monic, that the highest degree coefficient is 1. And then you consider fx mod fx, since this is a maximal ideal, the quotient ring is a field, and there is a map from f to this field, and this map has to be injective because it's a non-zero map. And so it is the vector as a vector space. You can check easily that is generated by 1x square up to x to the power n minus 1. Okay, so this is a field extension of vector space dimension equal to degree of fx. Okay, so we saw for PID irreducible and primary equivalent, in particular for Z also irreducible. So that's why in Z the irreducible and primes are the same, except for the for any non-zero prime ideal is a maximal ideal. All these things are true over Z. So next definition is associate. Uh, yeah, so associate in an integral domain. So let me give this definition. So two elements A not equal to 0, B not equal to 0 in integral domain are said to be associates if there exists U belong to A unit such that A equal to, in fact, u times p. I don't even need to say whether they're non-zero or not. So you take two elements in an integral domain, they are said to be associate if they differ by unit. Okay. And yeah, so maybe I'll discuss. So it's not true that in every integral domain irreducibles are primes. So let me discuss an example of that. Yeah, so now with this definition, so two elements are said to be associate if they differ by unit. Now we are ready to give example of irreducibles that are not prime. So consider the ring z root minus 5, which is inside C, and we have seen this is addition. This is, so it was a plus b root minus 5, where a and b are in Z. So because it is inside C and we have the addition and multiplication of complex number, this is an integral domain. So it sits inside a field, and field is an integral domain, so it doesn't have zero divisors. So in particular, because it's subset of C and the same addition multiplication, it cannot have zero divisors. Okay. So now we'll give examples of irreducible here, which is not prime. So you consider 6 equal to 2 into 3, and it's also equal to 1 plus root minus 5, and 1 minus root minus 5. Right? So we have this identity. Now look at 2. I'm claiming 2 is an irreducible. So suppose 2 equal to alpha times beta, where alpha and beta are in z root minus 5. So I'm saying if you write like this, one of them will be an unit. So what are the units in z root minus 5? So let's say a plus b root minus 5 into c plus d root minus 5 equal to 1. Then I can take conjugates on both sides. So I get a minus b root minus 5 into c minus d root minus 5. That is also equal to 1. So together we get a square plus b square, 5b square into c square plus 5d square is equal to 1. Now a and b are integers. So 5b square is greater or equal to 5. So each of this quantity are greater or equal to 1. So this will imply a square plus 5b square equal to plus minus 1. Plus minus 1. But it can never be minus 1. So in fact, because it's a positive, these are integers, so this has to be plus 1. Right? So and then also what is the option? If b is non-zero, then this is already more than 5, so this cannot happen. So a equal to plus minus 1 and b equal to 0. So this, note that implies this, which implies this. So units in z root minus 5, this ring are plus minus 1. These are the only units. So now let us come back to this equation 1. So you write 2 equal to, again, let's say alpha equal to, so in 1, say alpha equal to a plus b root minus 5, and beta equal to c plus d root minus 5, where a, b, c, d, these are integers. Here is a, b, c, d are integers. Okay, so this implies that so 2 equal to a plus b root minus 5, c plus d root minus 5. So again, I can take conjugate. Left hand side, I only get 2. So you get 4 equal to a square plus 5b square into c square plus 5d square. Okay, now if a square plus 5b square, what are the possibilities? These are integers. So a square plus 5b square can be 1, 2, or 4. Similarly, c square plus 5d square can be 1, 2, or 4. If this is equal to 4, then c square plus 5d square is 1. And then I saw c is plus minus 1 and d is 0. So that will mean it's a unit. Beta is a unit. So 2 will be irreducible. Similarly, if this is equal to, so this cannot be 4. If this is 1, then again so this implies, uh, so we can assume that a square plus 5b square equal to, so can assume that we are trying to show that it is irreducible, and in that purpose we can assume that these are uh, that this is equal to 2, and that is, but then also what is the possibility? So if b is non-zero, it's not possible. So b is 0 and a square equal to 2. So that's not possible. Okay, so this implies that 2 equal to alpha beta, then either alpha is a unit in z root minus 5 or beta. So this implies that 2 is an irreducible in z root minus 5. Right? Now let us prove that this is not a prime. So you again look at this equation, call this star or something, right? So you have a product of two elements, 6. 6 belongs to the ideal gen by 2 because 6 equal to 2 into 3. So 6 belongs to the ideal gen by 2 in z root minus 5. So this implies that 1 plus root minus 5 into 1 minus root minus 5. The product is 6, so belongs to the ideal gen by 2. Right? But so if 1 plus minus root minus 5, so let's say plus equal to 2 into c plus d root minus 5, let c comma d belongs to z, then you get 2c equal to 1 by equating both sides, which implies, which is a contradiction. C equal to half, it's a contradiction. So that means that means that's not possible. So the conclusion is that so this implies that 2 is not a prime ideal in Z root minus 5. So that there exist irreducibles. Similarly, you can show for 3 also, which are not prime in an integral term, Z root minus 5. So this will be the central question we'll be studying in our. So we'll be, as I said, we'll be studying quadratic ring kind of thing, and we want to understand when this happens, when some irreducible need not be prime. Okay. So 2 is an irreducible element, but it's not a prime. So we saw in every integral domain primes are irreducible, but irreducible need not be prime. This is an example. But in a PID, we have seen irreducible subprimes. Okay. In fact, in a PID, every non-zero prime ideal is a maximal ideal. So let us see what is the proof of that. Okay. So in a PID, every non-zero prime ideal is a maximal ideal. So let us see how to prove this. So let P not equal to 0 be a prime ideal in a PID A. And suppose P is contained in ideal M, which is a maximal ideal. Then we want to show that P equal to M. But because it's a PID, the every ideal is principal. So M is generated by single element M. So, and then in particular, by definition of maximal, it cannot be the whole ring. So, M is not a unit. So, again, the proof is similar to the previous one we did. So, P belongs to the ideal generated by M. So, P can be written as lambda times M, where lambda is in. So, P equal to lambda times M. Lambda belongs to uh, okay. Lambda belongs to A, right? It's a PID. So, yeah, M is not a unit. So, uh, Now P divides lambda because P is a prime and it is equal to lambda m. In particular, it divides lambda m. So P will divide lambda or P will divide m. So either case P. The either case either P is equal to you have if P divides lambda, then lambda equal to mu times m, mu times P, or if P divides m, then it is equal to beta times, or it is equal to beta times thing for for mu and beta are in this ring A. So either case you can cancel P from both sides, right? So lambda is a unit or mu is a unit in this case, right? In this case, m is a unit, that's not possible. If P is equal to mu times Pm, if P divides lambda, then we put lambda equal to mu P for some mu in A. So P equal to lambda mu times Pm, so you cancel P from both sides, right? P into 1 minus mu P, mu m equal to 0, but it's an integral domain. So P cannot be 0, so 1 minus mu m equal to 0, which means m is a unit. That's not possible. So the only possibility is that P divides m. So you input m equal to beta p. Then similarly, you cancelling p, you get lambda is a unit, right? So m. So then m and p are the equal. So that means m is a max. This implies that p is a maximality in A. So in a PID, every non-zero prime ideal is maximum. Like in Z, every non-zero prime is a maximal ideal, right? So I wanted to discuss some examples of maximal ideals in polynomial ring. So examples maximal ideal in Cx and Rx. Okay, so I want to discuss maximal ideals in Cx and Rx. So we have seen that any irreducible polynomial gives rise to a maximal ideal. Ideal in Fx for any field F, including F equal to R or C. This is true. And it's a vice versa, because if you have a maximal ideal, then that is singly generated by a single element. So it's generated by one polynomial, right? Uh, so if M is a maximal ideal, Fx, then M equal to some Fx, and Fx is an irreducible polynomial. So this first step, that M equal to Fx, is because it's a PID, so it is generated by a single element, and that element is non-zero because fx is not a field. So x did not have an inverse, so this is not a field. So degree, you can say degree of fx is greater or equal to 1. Fx is not equal to 0, in fact a non-constant polynomial. So fx is a maximal ideal in particular prime ideal. So fx is a prime, in particular it's irreducible because any prime is irreducible. So fx is an irreducible polynomial. So what are the examples of this? Uh, so uh, 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 so let us see examples of this. So we have to find irreducible polynomials. So for example, in Rx, so Ax plus B, where A is not equal to 0, is a maximal ideal. We have seen in fact in any fx, right? So it is A into x plus x minus b by A. So this ideal is same as ideal gen by x minus b by A. So I can write is of the form x minus c. C belongs to F. So these are all maximal ideals, right? So this we have seen example before. So these are all maximal ideals. So question is, so in particular x minus c, where c belongs to R or c belongs to C, are maximal ideals in Rx and Cx. Question is, are there any? So we have seen actually example that Rx mod square plus 1 is isomorphic to C. So in Rx there are other maximal ideals. So x square plus 1 is a maximal ideal in Rx. Okay. But what about Cx? So Cx, if you have irreducible polynomials, so this is called fundamental theorem of algebra, if you recall. Every irreducible polynomial every polynomial fx in Cx has a root in Cx. Sometimes it is also called C is algebraically closed. Right? This is called fundamental theorem of algebra. So the proof is usually the proof cannot be done only by algebra. Proof usually uses some analysis, although it's called fundamental theorem of algebra. But to use some analytic property of C, usually, some analytic property analysis on C you have to use to prove this statement usually. So using that so if you have a polynomial of degree greater or equal to 1, then it cannot be reducible because it has a root. So the only maximal ideal, right? So only maximal ideals. So in only maximal ideals in Cx are of the form, let's say, 2. This is written out of the, okay, so let me just simply write x minus c So see this contrast. In C, the only maximal ideals are given by linear polynomials, but that's not the case over R. R, you have x squared plus 1. In both cases, linear polynomials, x minus lambda, lambda is in the field. Maximal ideals in any field, but in R, you could have quadratic polynomial like x squared plus 1. But you can have more like that. But in C, you cannot, that's not the case because of C is algebraically closed. Here you see x squared plus 1 has no root in R, but x squared plus 1, for example, is split as x plus I into x minus I. And both x plus I and x minus I are maximal ideal in C. Okay. So next time we'll introduce this concept of UFD and see some properties.